Swayam Prabha. Digital India. Educated India.
Okay. Oh, good morning. I want to talk this morning about the area of visual analytics. This is an area that is attracting a lot of interest with all that is happening in the area of artificial intelligence and machine learning. It is a big area on its own, and it is an important area because it tells you that it is important to obtain information or extract information from your data in the way you display your data. So let's look at what this means. John Tukey, who did a lot of work on signal processing and other areas, made a very famous quote, and I share this with you. Start of quote: "The greatest value of a picture is when it forces us to notice what you never would have expected to see." End of quote. And this is what data visualization does. If you display your data effectively, it will reveal a lot of interesting information. So we say that data visualization takes analytics, which is how we extract information from your data. It takes analytics to a whole new level. The main message in my talk then is display your data. Don't bury your data. Don't let it just sit in the archive files or on your flash drives. Display your data effectively so that it conveys patterns and useful information in your data. The other important point I wish to make is one should look at all the data cohesively and collectively. What I mean by this is, don't simply look at singular trends of your data. Look at all the data collectively. So look at the data in a multivariate framework, because the real world is not univariate. The real world is multivariate. Here is an example where I show you collectively the temporal or the time trends of 37 different process tags. This is data that has been collected from a real industrial process. And what you notice when you plot your data collectively is that there are many variables that are oscillating almost at the same frequency as I show you here. And many of these variables are oscillating continuously for the total duration of this plot, which is roughly 500 sample instants. So when you plot your data cohesively, collectively, it gives you this interesting information. So this is an example where we are not simply looking at singular trends of the data, but we are looking at all the tags together. So we are looking at the data in a multivariate framework. The other important point to note is that it is also important to show the data not only in the temporal domain, but also in the spectral domain, if the data allows you to compute the spectral counterpart of each variable. And I show you that here. So here are the selected few time trends on the left-hand side, and the corresponding spectral plot of the data is shown here. And what you notice is that many variables are oscillating at the same frequency, roughly this frequency, which is 0.008 or 0075 normalized frequency. So quite a few variables are oscillating at the same frequency, and you see that here as well in the temporal domain. And on the top left hand side, I show you a layout of the process. And the intent of this exercise in data visualization is to try and find out what, if any, of these variables are the root cause variables which are causing these oscillations that are propagating throughout the plant. Now, another way of looking at data is to compute the correlation coefficient and display the correlation coefficient in this manner. And I show you the numerical values of the correlation coefficient. The diagonal elements of the correlation coefficient, as you would expect, are ones. Each variable is highly correlated with itself, or perfectly correlated with itself, and that gives you the ones along the diagonal element. And then this variable here is the correlation coefficient between tag 1 and tag 2. Here is the correlation coefficient between tag 1 and tag 3, and so on. And the intent in showing this is that these numbers don't really give you the kind of information that you're looking for. So we're simply generated more numbers from the time trends, and the idea is don't simply generate more numbers to try and extract information. So the main message here in this slide is that when you're looking at all the correlation coefficients, it doesn't give you more information. It's like looking for a needle in a haystack. It's pointless to do this. So without proper analytic tools, such an exercise generates more debate, more heat. It does not give you the insight that you're looking for. It does not shed more light in the analysis exercise. What you can do, though, is you could convert these numbers into colored pixels, and we've done that just here. We've generated all of those numbers into colored pixels, and we've obtained the absolute values of those correlation coefficients. So whether the correlation coefficient is negative or positive doesn't matter. We just want to look at which variables are most highly correlated with others in the absolute sense. And here is the scale. The scale here with the red and the orange colors shows variables that are most highly correlated with others in the temporal domain. So not only have we done that, we've also reordered the variables and grouped them or clustered them so that the most highly correlated variables are located together. So I show you here. Variables 17 and 18 are most highly correlated, as are variables 35 and 36. And then here you have a group of 4 variables, 3, 4, 20, and 34, that are also quite highly correlated with others. So this is the exercise of turning your temporal correlation coefficient matrix into a correlation color map. If you, however, choose to do the same thing but in the spectral domain, if you choose to look at the data in the spectral domain and generate a spectral correlation map. Another simple way of looking at this is to ask the question, which spectral shapes are shaped similarly? And what you get is this clustered spectral correlation map with the same scale on the right hand side, and it's showing you that some variables, these variables 5, 21, 22 and 31 are very highly correlated with each other, meaning their spectral shapes are very, very similar. They're almost identical. In other words, those four variables are oscillating at the same frequency. Here is another group of variables, 7, 12, 35 and 36, which also are highly correlated with each other in the spectral domain, and it's also showing those variables also have similar spectral shapes. And here is this very large group of variables which are also quite highly correlated with each other, and they also have a similar and yet a different spectral shape. So this allows you to identify the variables of interest, and if we go back to the previous slide, if you're interested in looking at which variables are oscillating at the same frequency and what might be the corresponding root cause, then we would be able to say, okay, it is this spectral shape here, and we can shortlist the variables of interest to find the root cause. So I show you here a real industrial case study. This is the benchmark Eastman Chemical data set, where the dotted variables were all oscillating at the same frequency, and we were assigned the task of finding out the potential root cause of these oscillations. It's important to remind you that in a highly integrated process flow sheet, oscillations need not simply start upstream here and propagate downstream. They can even start downstream, and because of recycle, they can show up upstream. So this is a tricky problem, and the analysis of data in the temporal and spectral domain helps you to shortlist variables that may be the root cause. So we're looking for the root cause detection of these plant-wide oscillations, and what we do is plot all the important variables in the time domain and also look at them in the corresponding spectral domain. And now identify the variables that are oscillating at the same frequency. In other words, they have the same spectral shape, and let's look at those variables, and I show that here. So these are all the variables, and we've clustered them. So this is the clustered correlation map of all those variables in the spectral domain. And now if the frequencies of interest is as shown here, then we can look at all of these variables to identify which may be the root cause of these variables, of these oscillations. So we looked at that short list. Here are all the variables that are oscillating more or less at the same frequency. The frequency of concern in this example was this is on a logarithmic scale, so it is 0.002 or 0.025 cycles per sample. Here are the corresponding variables, and rather than looking at all of those 37 or more tags, we only need to look at fewer number of tags to find out what the root cause of these oscillations may be. So the purpose of looking at this exercise is to simply say, look at the data cohesively, collectively, look at the data in the temporal domain, also look at the data in the spectral domain, if that is the purpose of the exercise. Another way of looking at the data is to look at scatter plot of the data. And I show you this plot. These are different. This is a different data set. This is another benchmark data set in MathWorks. It's the car or the automobile data set. There are 5 variables of interest, and what I show you is the scatter plot matrix that is generated for those 5 variables. The diagonal plots shown here correspond to the distribution of each one of these variables, and it serves to show that the distribution is non-normal as shown here. It is normal here, non-normal here, non-normal here, and so on. And then this is the scatter plot of variable x1 versus x2. This shows that x1 versus x3 is negatively correlated. Similarly, x1 versus x4 is negatively correlated, and so is this negatively correlated. Here x3 versus x4 is positively correlated, and x4 versus x5 is also positively correlated. This is a symmetric plot, and we can also look at this data by using the graphic handle in MathWorks, in MATLAB. You can look at the data in a more descriptive way. There are 5 variables, and the distribution of each one of these 5 variables is shown along the diagonal elements. The 3 predominant variables in red, green, and blue show up quite decisively. These correspond to cylinders 4, 6, and 8 in this data set. This data set consists of the miles per gallon, the acceleration, the displacement, weight, and horsepower of cars that run on 4, 6, and 8 cylinders, and additional cylinders as well, corresponding to the turquoise and the magenta colors. Okay, so the scatter plot also gives you useful information, and we can also do another plot which is known as the parallel coordinate plot. And perhaps I can show this on the board to you. Let me explain to you what one means by a parallel coordinate plot. Generally we choose to display data as magnitude versus time. But if we have many variables, we can also do the following. We can display x1 like this. We can display x2 like this, or an x3 or variable 3 like this. So if we look at this plot from this angle, this perspective, the time value does not show up, and what you get is the following. So we have magnitude, and then we have, let me use the same color, x1 and x2 and x3. This is x1, x2 and x3. So at this particular point in time, we have this measurement, this value for x2, this value for x3, and at another moment we have this value for x1, this value for x2, and this value for x3. So we would then have, for each point in time, so this corresponds to T1. At another point in time, we might have, this corresponds to T2, and so on. So the parallel coordinate plot is simply a plot of all of this data in a different domain, okay? And so this plot that I showed earlier, all the data that was shown here, the corresponding parallel coordinate plot is as shown here. So here is the data, the coordinate value or the magnitude for miles per gallon, acceleration, displacement, weight, and horsepower. So everything is now normalized, and we show all of this data for 4, 6, and 8 cylinders. Okay. So again, this data does not have any time designation. In the example that I showed you, I had the time designation. So you can obtain a parallel coordinate plot for any multivariate system that you choose to work with. This plot is quite dense, and another way of looking at the parallel coordinate plot is to simply plot the mean value as shown here and the interquartile range as shown by the dashed line. And we will look at this in a more detail shortly. But so I show you here the parallel coordinate plot with the mean values and the interquartile ranges. And this plot is particularly useful if you want to do classification or clustering of this data. Now, we have not discussed clustering or classification, but let me pose this as a question. If we only have the data and the data is not labeled, meaning we have collectively data for different cars, and the information that we have is miles per gallon for each car, or the acceleration for each car, displacement, weight. Displacement is the displacement of the cylinders in the car, the weight of the car, and the horsepower generated. If we only have this data and we would like to know if the corresponding car has 4 cylinders or 6 cylinders or 8 cylinders. So if the data were unlabeled, so as to say, which variables would allow you to classify the data so that you are able to discern from the data that this car, based on the 5 variables of interest. Indeed, it has 4 cylinders or 6 cylinders or 8 cylinders. Well, it turns out the variables that show the greatest diversity is the weight and displacement and also the horsepower, because the corresponding magnitude do not overlap each other. Whereas acceleration here, the variables overlap each other, and this will not allow us to differentiate between 4, 6 and 8 cylinder cars. The miles per gallon can also be used as another variable for classification purposes. Okay, so again, the intent of these exercises is to show you different ways of displaying your data and extracting information and patterns in your data. Those 3 variables which allow you to differentiate easily between 4, 6 and 8 cylinder cars can also be plotted in a 3-dimensional plot as shown here. The vertical direction is the horsepower, and then the horizontal directions are displacement and weight. We've color coded the variables, so now you can easily cluster or classify the data into 3 separate groups. Here is group 1, another group, and then the third group. So this display also allows you to differentiate between the 3 data sets. Okay. Even if the data was unlabeled as shown here, you would notice by rotating the figure and looking at the 3D plot from many different points of view that there are 3 separate clusters. When you look at the distribution of the data, it's important to be reminded that the data that you display may not be normally distributed. It may not be bell-shaped as we usually think of the data. If it is non-normally distributed, then we need to be able to get some measure of the spread of the distribution. And for that, we have to look at what is the mode, the median, and the mean. When the distribution is symmetric, the mean, median, and mode are similar as shown here. The mode corresponds to the most frequent observation. The median gives the location such that 50% of the data is will be below that value, and 50% of the data will be above that value. The mean is the arithmetic average of all the observations. Now, the other important thing to note here is that some of this distribution as shown here, this one here, perhaps has a fairly large mean, fairly large standard deviation. This distribution here may have a smaller standard deviation. The 3 values, the mode, median, and mean for each distribution are color coded as shown here. Box plots are also interesting ways of displaying your data. And I show you a simple example here where we have income versus balance for people who owe money for credit cards. And the color code is people who default are shown in the orange crosses. People who do not default on their credit card payments are shown in the blue dots. So the plot of income versus balance, a bivariate plot, is shown on the left hand side. The corresponding box plot of the data for balance versus the default values is shown in the middle, and then on the right hand side I show you the income versus the default values of the same data set. If you were a banker and you were in charge of issuing credit cards and you wanted to know of the default history of the person who is applied for a credit card, then the important variable that will allow you to differentiate between whether the person has defaulted before or not is this plot here. Clearly, in this plot, the median value is shown here. The interquartile range is at the top here, and the bottom, and so the first interquartile range and the third interquartile range, and I will explain that to you in the next slide, are shown here. So clearly the balance will allow you to separate or differentiate between people who are likely to default or not default. The income will not give you that information. As you can see here, there are a few variables that are at the top range, and I will explain to you what these variables mean. These are likely outliers, and there are some outliers at the bottom for the people who've defaulted. Those correspond, these variables here correspond to the blue dots that you see. Likely the dividing line between people who are likely to default or not is somewhere here in the middle, between 1000 and 1500, somewhere here. So you can see that there are outliers, the blue dots here and the orange crosses on the left hand side, which are these outlier values here. Let me explain what those terms are. So here is the interquartile range details for the box plot. This is the box plot that we were looking at. Q1 corresponds to the first interquartile range. It is the median minus roughly 0.6745 times the standard deviation. The interquartile range 3, Q3, corresponds to the median plus 0.6745 times the standard deviation. And the data between Q1 and Q3 corresponds to 50% of the data set. Okay? Whereas if you look at the conventional plus minus 1 sigma, that contains 2/3 of the data. The box plots choose to only look at the 50% of the data set. You can adjust that. And then the bottom range of the box plot and the top range of the box plot corresponds to the first quartile minus 1.5 times the interquartile range, and then the top line corresponds to Q3 plus 1.5 times the interquartile range here. This is not exactly 3 sigma or minus 3 sigma, it is just under 3 sigma. So that corresponds to roughly 99.3% of the entire data set. So the data set between here and here, this is roughly 50 plus 24.65 times 2, So this is 99.3% of the data. On the other hand, when you look at plus minus 3 sigma, that corresponds to almost 99.9% of the data. So again, the box plots convey a lot of useful information, such as the interquartile range of the data. It also gives you an indication of the outliers, if any, in your data set. So these are all useful ways of looking at your data. Another way of looking at your data is to look at your data in the spectral domain, as we outlined earlier, but perhaps better than simply looking at the data, the fast Fourier transform of your data, the FFT of the data, you want to look at the data in the wavelet domain. I just want to show you, talk about the differences between the spectral domain and the wavelet domain. If you look at the data in the time trend as shown here, what I show you is 3 different frequencies associated with a signal. You have a low frequency signal here, you have a high frequency signal in the middle, and a mid frequency signal at the end. The corresponding spectral plot of this data identifies the 3 frequencies, the low frequencies, the mid frequency, and the high frequency. But when you look at this spectral plot here on the top right hand plot, the localization of the frequencies with respect to time, that information is lost. We don't know from this plot alone as to when did the low frequencies start. We don't know when did the high frequencies start. You can see that here in the temporal plot. But if you look at the wavelet plot of the same data set, it preserves the temporal and the spectral localization of the data. It tells you that you have low frequencies in the first 125 samples. It shows you have mid frequencies in the mid 125 samples of the data, and it shows you you have high frequencies in the mid in the 125 midpoints of the data, and mid frequencies in the last section of the data. And you can see that here as well in the scaleogram. So again, an example to show you the different domains of visualizing your data. You may also be working with binary data set. This is alarm data. An alarm is either on or off. And if you have binary data, meaning bunch of zeros and ones, you can obtain what we call a high density alarm plot. This is similar to the temporal domain plot of the data that I had shown you earlier, where we were looking at all the data cohesively and collectively. But here I show you a binary data plot of many variables. There are roughly 20 variables, and each pixel contains 10 minutes worth of data. We call this the high density alarm plot. It is rank ordered, meaning the variable with the highest number of alarms is variable 1, the second bad actor is variable 2, and the third bad actor is variable 3, and so on. Okay. So this plot, this high density plot, also gives you a lot of interesting information. It tells you or identifies for you the variables that have a large number of chattering alarms. It identifies for you variables that may be alarming together, indicating that perhaps these are redundant alarms. And if you have vertical upsets, all the alarms occurring more or less at the same time, that is telling you that there may be a major plant upset in that variable. Okay. We can also look at all of the alarm data collectively, and I show you this in this plot here, where we have identified or obtained a sum of all the alarms with respect to time. So here is the number of unique alarms versus time, and the time duration of each one of these alarms with respect to time, and we can convert all of those alarms into what we call a spiral plot. This is an interesting way of looking at alarm data, and I give you this example to simply show you that you can always come up with new ways of displaying your data, new and unique ways of displaying your data, so that you see the information that you would not have expected to see before. And I want to share that with you here. We have roughly 90 days of data for alarms in a process over a 24-hour period. So what we have here are 90 concentric circles. This is data for day 1, data for day 2, and so on, and this last concentric circle is data for day 90 on a 24-hour clock. And the color code essentially tells you the number of variables that were alarming at the same time, and we call these alarm floods. So it's important to note that between 9 a.m. to 3 p.m. you have consistently a large number of alarm flood events occurring almost daily over that 90-day period. Whereas during the night time of operation you have fewer number of alarms. Here too you have fewer number of alarms. Here too you have fewer number of alarms. This data was collected in 2017 between January 1st and March 31st. If we look at the same data over the same 3-month period, but in year 2, in 2018, after a number of changes were made to the plant, we obtain a much better picture. Now all of those alarm flood events don't show up. We do have some alarms here in the afternoon, but more or less we have fewer number of alarms or fewer number of process upsets in this process plant. So another way of displaying data and showing you the information that you would not have expected to see otherwise. Okay. Collectively, for this entire 90-day period, we can also look at all of this data on a 24-hour clock, and it tells you the number of alarm events, flood events that occurred in the morning starting at 9 a.m. up to 3 p.m. Those are the large number of alarm events or process upset events that occurred on this plant. There were very few upset events in the evening or in the early hours of the morning. Okay. Again, another way of looking at data. So to conclude, what I want to say is that visual displays are a powerful way of extracting information from your data and displaying information from your data. It's a powerful way of conducting analytics. And the way you want to do this is to examine and display data in a multitude of domains. And I showed you examples of looking at data in the temporal domain, spectral domain, as bar plots, box plots, in parallel coordinate plots, as distributions of each variable, and so on. Look at the data in a multivariate framework. The real world is not univariate. The real world is multivariate. And leverage and maximize the value in your data that's sitting in different files. Look at the data cohesively, collectively. Unload all of those files and plot all the data together. And look for patterns and information in your data. Examine your data carefully. Thank you. And that ends this presentation.